Okay, so here we are, the next day of our, third day of our e-learning, and we're going to look at the nature of solids. And you can see we've done gases and liquids, and those other videos were posted. You can check those out. But now we're going to talk about solids. So what is the strongest material in the world? All right, and some people could give me a lot of options. It's not steel or any kind of plastic, but it's carbon, and it's carbon known as fullerene, and we'll look at fullerene. But this fullerene is put in the small tubes called nanotubes, and this is the strongest material that we know. In fact, there's been talk of making a cable, like a wire, that goes from the Earth to a satellite somewhere in orbit, and we could suspend that satellite with the nanotubes. If that will ever happen, I don't know, but there's belief that the nanotubes could hold that satellite in place that far from the Earth. Okay, so let's come up with a model for solids. What structure and properties, and how are they related with solids? Okay, so general properties of solids reflect their arrangement of particles and the locations, which are fixed, which means they don't move, of their particles. In most solids, the atoms, ions, or molecules are packed tightly together. They're dense, not easy to compress, so they're packed together. Not easy to compress, very dense. And the solids vibrate, but they stay in a fixed point, so they do not flow, all right? Liquids flow, solids do not. When you heat a solid, though, the particles do vibrate, and when they vibrate, kinetic energy increases. And when that kinetic energy gets to a certain point, the particles then begin to flow, which then makes them melt. So it's the temperature where a solid changes to a liquid, so where the particles gain enough kinetic energy to change form. Okay, at this temperature, the vibration particles are strong enough to overcome the attractions that hold them in fixed positions. So this is where the particles move fast enough to flow. The opposite of melting is freezing. The freezing point is where the temperature where a liquid changes to a solid. Okay, here's a key point, and I'm going to circle this whole thing because I want you to see it. The melting and freezing points of a substance are at the same temperature. If if we melt ice at 0 degrees Celsius, we also freeze at 0 degrees Celsius. And at some point we'll do lab and you'll see that happening. But this melting freezing point is the same. It just depends if we're adding energy or taking away energy. Okay? So what we get at this melting freezing time is something called an equilibrium. So when we heat, the solid goes to liquid. When we cool, liquid goes to solid. But this occurs in water at 0 degrees Celsius, both melting and freezing. In general, ionic solids have high melting points. Ionic, okay? High melting points because of the strong forces that hold them together. So salt, for example, sodium chloride, has a high melting point. The melting point is 801 degrees Celsius. That's extremely high. So sodium chloride has a melting point of 801 degrees Celsius. Molecular solids have relatively low melting points. So like water, anything that's plastic, hydrogen chloride, which is it melts at negative 112 degrees Celsius, okay? So most of the time hydrogen chloride we see as a liquid, right? Because it melts at such a low temperature. But ionic compounds, high melting points. Molecular compounds, low melting points. Explain why solids do not flow even though their particles are constantly moving. They don't flow because of they're tightly packed. They're at fixed points, we call that. These particles stay and rotate here, but the particles stay close together. And by staying together, they cannot flow. Okay, so what determines shape of a crystal? I'm not going to go into great detail on this, but we need to know what these crystal structures at least are identified as. So in a crystal, the particles are in a three-dimensional repeating pattern, okay? We call this pattern a crystal lattice. So it's a repeating three-dimensional pattern. For example, here's table salt. Again, you have positive sodium, negative chlorine, positive sodium, negative chlorine, and they alternate. And this pattern then gives us a shape, okay? These ions are vibrating slightly, but they are attracted to each other, the positives to the negatives repelling the positives, or negatives repelling the negatives, but you can see that the negatives and positives touch, but the positives and the negatives don't touch each other. And that's because opposites attract, like repel. The shape of a crystal depends on arrangement of particles, and there's all kinds of, you can spend a lot of time looking at shapes. The smallest group of particles we call a unit cell. It has a geometric shape. A crystal lattice is just a repeating array of the different kinds of unit cells, and you can see there are 14 kinds of unit cells. Okay, we're not going to talk about them, but just understand that there are a lot of different types of unit cells, but we keep those repeating, and then what we do is we end up making a crystal system. So here are different crystal systems. The first is a cubic, all right, and that's pretty simple, a straight cube. Body-centered, it's a cubic unit with something in the middle, usually an ion, but it could be an atom in the center. And then face-centered, where you have one face that has 1, 2, 3, 4, 5. And then we have those faces all are in a cube. All right? Just different types of unit cells. So these are different crystal systems that you see. All right? Simple, body-centered, face-centered. All right, another term, allotropes. Now, there are some substances that can exist in more than one form. All right? And carbon is one of those things. Carbon's an allotrope. Carbon can exist as a diamond, which is a crystal form. We have graphite, which is another type of carbon. And then in 1985, we've actually formed and discovered a new form of carbon once our technology got better so we could see it. It's called Buckminster fullerene. And I'll show you a picture of what that looks like. But carbon can form different things, and so carbon is an allotrope. So here's a diamond. Each carbon is strongly bonded to 4 others. This is a very compact structure, okay? Very compact. And they're really tight together, and that's why diamonds are so hard. Graphite, the atoms are in hexagons connected to each other, but they're spaced apart, and this opening allows carbon to, or graphite to have some of that dust that comes off. Graphite spray is used as a lubricant. But graphite is all pure carbon. It's just formed differently. So the same carbon that makes up graphite makes up diamonds. And then Buckminster fullerene, you can see this. It's the shape. It's like a soccer ball. The carbons are arranged in pentagons and hexagons, and it's a hollow sphere. And this was discovered again in 1985 by Buckminster. And so this, and this are all carbon-based compounds. It just depends how this unit cell's set together to determine what its function is, or what its shape it's going to be. The physical properties of diamond and graphite and fullerenes are quite different. Diamond, high density, very hard. Graphite, low density, and soft and slippery. And fullerenes have strength and rigidity. And the fullerenes are what would make that cable that I talked about here at the beginning. You'd use the fullerenes with the carbon to make that. So all carbon, but entirely different physical properties. Chemically, all carbon. Physically, high density and hard, low density, soft and slippery, or very strong and rigid. So allotropes are 2 or more different molecular forms of the same element in the same physical state. So these are all allotropes of carbon. Okay? Diamond, graphite, and fullerenes. Although allotropes are composed of atoms of the same element, they have different properties because their structures are different, and we looked at the structures previously. Only a few elements have allotropes. In addition to carbon, phosphorus, sulfur, oxygen, boron, and antimony are all elements that have allotropes. And when we look at this one, O2 and O3, this is the oxygen we breathe, and this is the ozone that protects us from getting fried by the sun. Okay, so what structural properties make fullerene nanotubes the strongest material in the world? And it is because this covalently bonded to 3 other carbon atoms, the structure creates a cage or loop. So you got this cage here in this structure. The shape allows force to be distributed evenly across the surface so that the entire structure can hold the force. And if that force can get evenly distributed amongst all these atoms, it's very strong, and you can hold up great things like a satellite from the surface of the Earth. Another thing that comes up is some solids aren't crystals. Some are what we call amorphous. Now, this is a small number, but some are amorphous. Amorphous solids don't have these crystalline structures. They're not ordered. Examples of amorphous solids: rubber, plastic, asphalt. These are solids, but they're not crystalline in nature. Their atoms are randomly arranged. There's no set pattern. Another example is glass. It's a product of silicon dioxide in heat, and what we do with that is it becomes a solid, and this solid then is cooled to a rigid state, but glass isn't crystals. Another name for glasses, they call them super cooled liquids. If you've ever seen how glass is made, you can Google it. You can see why that is. So what's the difference between an amorphous solid and a crystalline solid? Particles in a crystalline solid are orderly arranged. Amorphous solids are randomly arranged. Okay? Crystalline, orderly. Amorphous, randomly arranged. Key concepts, you can read those again. Words. Melting point, freezing point, crystal. You should know what those words are. Unit cell, allotrope. You should know what those are. Amorphous solid, and then glass, which is an example of an amorphous solid.